Hello, Chem 2 class. This is my Chapter 14 study guide review. Um, I'll go ahead and, let's go ahead and get started. I'll minimize me, and let's see. I think I'll put me down here. Alright, I think I've minimized me enough. Okay, alright, that being the case. Alright, so the first one, problem, the units of a reaction rate. Now, reaction, it's a rate, so you'd expect it to be something with per unit time per second. And you guys know, because I told you, it's going to be moles per liter per second. But of course, that can take the form of a lot of units. Of course, I could have m times s to the negative 1, or I could have moles uh, per liter, or L to the negative 1, S to the negative 1. So the answer, of course, is going to be E. All right. Number 2, it says the appropriate units for first order rate constant are, and in order to answer that, I'm going to go to the chapter 14 PowerPoint. Now remember, we said the units for the rate constant, so all you got to do is, if the overall order is whatever the overall order is, all you got to do is subtract 1 from that. Okay, and you're going to say m to the negative of that number. So if it's second order, 2 minus 1 is 1. So it's going to be m to the minus 1, s to the minus 1. If it's third order overall, it's going to be 3 minus 1 is 2. So it's going to be m to the minus 2, s to the minus 1. So you're going to always have that s to the minus 1. And remember that m stands for moles per liter. But if it's negative, that means it's in the denominator. So, for example, m to the negative 1 is liters per mole. Okay, so if it's m to the negative 2, would be liters squared per mole squared per second. Okay, if it's m to the negative 3, it would be liters cubed per mole cubed per second. Okay, so just keep that in mind. All right, so the answer to that, so for first order, is going to be, of course, s to the negative 1, or it's going to be reciprocal second. So the answer to that is going to be C, right? Okay. All right. So number 3 is the appropriate units for second order rate constant. Again, we know it's going to be 2 minus 1 is 1, so it's going to be m to the minus 1, s to the minus 1. Now we know if it's m to the minus 1, that's going to be liters per mole. In this case, the units that they gave us are m. So m to the minus 1 is going to be reciprocal. So m in the denominator and s in the denominator, since they're both to the negative 1 power. So the answer there is going to be B. Number 4, the appropriate units for third order rate constant. Again, we know 3 minus 1 is 2. So it's going to be m to the minus 2, s to the minus 1. So it's going to, and of course, since it's minus 1, it means that those terms are in the denominator. So it's going to be 1 over m squared times s. So the answer to that is going to be D. All right. So 5 is the first problem where we actually we might need to do calculations. I don't see. Let's see. I'm going to go ahead and snip this bad boy and see what we get here. I think I'll snip the entire problem. All right. And I ain't got time. Okay, for the reaction, let's see what I have here. Bromate, 1 mole of bromate is reacting with 5 moles of bromide and 6 protons, 6 moles of proton. Give me 3 moles of bromine and 3 moles of hydrogen. At a particular time, the change in the bromate concentration with respect to the change in time is a negative 1.5 times 10 to the negative 2 moles per liter per second. Okay, it's a reactant. Of course, the concentration is going to decrease with time, so it is going to be a negative number. Okay, so they want to know what is 1/3 the change in the bromine concentration with respect to the change in time. So we know that the conventional way of reporting the rate, okay, if we take a product that has a stoichiometric coefficient of 1, the change in that concentration with respect to the change in time is a conventional way of reporting the rate. So you say, well, what if you don't have a product with a stoichiometric coefficient of 1? Well, that's okay too, all right, because I know that, for example, the products that I have right here, I have bromine and water. So they're going to appear 1/3, well, 3 times as fast as this hypothetical product with a coefficient of 1 appears. So all you got to do to get the conventional way of reporting rate is divide it by 3. So 1/3 times the change in my bromine concentration with respect to the change in time is equal to the conventional way of reporting rate. Okay, so I'm going to put rate right there, which is also equal to 1/3 in this case times the change in my H2O concentration with respect to the change in time. All right, so those are my products. Now my reactant, well, I have my bromate. Now since the reactants, their concentration decreases, we have to stick a negative in front of it. Okay, but still the same thing holds. Bromate, the stoichiometric coefficient is 1. So the change in my bromate concentration with respect to the change in time, a negative of that is also the conventional way of reporting rate. And I might as well go ahead and put my bromide down here too. A negative times 1/5 times the change in my bromide concentration with respect to the change in time. That's equal to a negative 1/6 times the change in my proton concentration with respect to the change in time. All right. Now, I know I didn't have to do that because we're just trying to relate a bromate concentration with a bromine concentration, so I could have left all those other ones out. I could have just put this up here. The rate is equal to, let's see, I'll just put a negative of the change in the bromate concentration with respect to the change in time. And of course, set that equal to 1/3 the change in my bromine concentration with respect to the change in time. Okay, now they give us the change of the bromate concentration with respect to the change in time. Notice they did not give us the negative of that. They didn't give us this, they just gave us this part inside without the negative. So I'm going to say my rate is equal to a negative times a negative 1.5 times 10 to the negative 2 moles per liter per second. Now that's equal to 1/3 times the change in the bromine, I should say. I left my 2 off there, didn't I? Times the change in time. All right. Okay, now they want us to find this, the 1/3 of my time, the change in my bromine concentration with respect to time. So you mean all I have to do is take the negative of a negative and get a positive? So I'm going to get the same number, 1.5 times 10 to the negative 2 moles per liter per second. Yeah, that's what you get. So the answer is 1.5 times 10 to the negative 2 moles per liter per second, right there. But okay, in order to get that, I did have to write out these equalities. So it's just algebra. Okay, it's just algebra. That's all it is. So, all right. So going back to the PowerPoint, let me see the lecture notes. Let's see. Number 6. For the following reaction, the change in my H2 concentration with respect to, okay, guys, remember that the partial pressures, if it's a gas, the partial pressure is proportional to the concentration. So we can use partial pressures in lieu of concentration. Okay, if you guys remember the ideal gas law, let me go back to it. Okay, of course, PV equals nRT. So if I divide both sides by V, I get P is equal to nRT divided by V. N divided by V is the molarity. So I'm going to say P is equal to molarity times RT. So yes, the pressure is proportional to the molarity. The constant of proportionality is the temperature times the gas constant. Okay, so that means I can use pressure in lieu of molarity when I do these problems. So I should be able to do number 6 no problem, and I'm going to go ahead and do a full screen snip. go back to my whiteboard, clear canvas, and go ahead and paste. Alright, so for the following reaction, the change in my H2 concentration with respect to the change in time was found to be 2.48 times 10 to the negative 2 atmospheres per second. Okay, now let's see what I have here. Let's see. So it looks like we're reacting heptane. We're reacting. Well, no, that's not heptane. C6. No, hexane. We're getting hexane, and we're getting. Let's see. We're getting some benzene and some hydrogen gas from it. So we're oxidizing hexane. All right. So yeah, we're getting benzene and hydrogen gas out of it. All right. So for this reaction, yeah, they left a lot of stuff off about this reaction, didn't they? Okay, for the following reaction, now we know the change in the H2 concentration with respect to the change in time was found to be 2.48 times 10 to the negative 2 atmospheres per second. They want us to find the change in my benzene concentration, the partial pressure of my benzene with respect to the change in time. Okay, so it's not that problem, not that big of a deal. They're both products. I don't have to worry about the hexane, so I'm not going to worry about it. So I'm just going to go ahead and write the rate is equal to the change, since they're both products, the change in my, let's see, the change in the partial pressure of C6H6 with respect to the change in time, and that's equal to, let's see, 1/4 times the change in the partial pressure of my H2 with respect to the change in time. Okay? All right, so we got the equality down. Now they gave us just this part right here. They gave us this part. They didn't give us the whole thing. They gave us this part. So if you want to just go ahead and say, well, the change in the partial pressure of benzene with respect to the change in time is equal to 1/4 times 2.48 times 10 to the negative 2 atmospheres per second. Okay, y'all want to say that? Now, yeah, all they asked us to do is find the change in the partial pressure of benzene with respect to the change in time. So all I got to do is take this number and divide it by 4. So let's go ahead and do that. So I'm going to get so 0.0248 divided into 4 equal parts. I end up with 6.20 times 10 to the negative 3 atmospheres per second. Okay, and that corresponds to A, doesn't it? Yay, A. All right. So let me go ahead and clear the canvas, and I will, let's see what we got here. Number 7, for the hypothetical reaction, A plus 3B yields C. The rate of appearance of C given by the change in the concentration of C with respect to the change in time may also be expressed as, all right, so notice that C is a product, okay? And the stoichiometric coefficient is 1. So the change in the concentration of C with respect to the change in time is a conventional way of reporting the rate. So all I got to do is relate A and B to that. So I'm going to say that the rate, the conventional way of reporting the rate, is going to be equal to a negative of the change in my A concentration with respect to the change in time, which is equal to a negative 1/3 times the change in my B concentration with respect to the change in time. Okay, so so all I got to do is find which one of these, this term or this term, is going to be up here. So of course I see the A term, the change in the A concentration with respect to the change in time, but the negative is not there, so it's not A. B is not 3 times the change in the B concentration with respect to the change in time, so exclude B. C is a negative 1/3 of the change in the B concentration with respect to the change in time. That's the right answer, right? It's going to be C, because this and this are the same thing. And of course, it's not going to be D, where you have a negative 1/3 of the change in A concentration with respect to the change in time. We know it's not going to be that. Okay, so let's see. Number 8, for the overall chemical reaction shown below, which one of the following statements can be rightly assumed? Okay, so let's see what we have here. We're reacting hydrogen sulfide, a very smelly, stinky compound, by the way, with oxygen, and we're forming sulfur and water. Okay, now just from the reaction as given, you cannot determine that the reaction is third order overall. You can't determine anything about the reaction unless you do experiments. Okay, you're going to do some use your integrated rate laws, or you're going to do initial rates experiments to determine what the rate law is. So it can't be A. The reaction is second order overall. It can't be B. The rate law is okay. You can't determine anything about the rate law. Okay, just from the reaction. It can't be D either, because like I said, you can't determine anything about the rate law from the reaction just by looking at the reaction. E, the rate law cannot be determined from the information given. Okay, yes, that would be the right answer, wouldn't it? Okay, now remember, like I told you guys in class, that the stoichiometric coefficients, unless it's an elementary reaction, they have no bearing on the orders whatsoever. Okay. All right, and we know it's not an elementary reaction because we have 1, 2, 3 molecules involved in this bad boy, right? Thermomolecular reactions are very, very, very rare. Okay, thermomolecular elementary reactions, I should say, are very, very rare. Okay, number 9, the reaction A plus 2B yields products has been found to have the rate law. Rate is equal to K times the concentration of A times the concentration of B squared. So it means it's first order with respect to A, second order with respect to B, third order overall. While holding the concentration of A constant, the concentration of B is increased from X to 3X. Predict by what factor the rate of the reaction increases. Now notice A was constant, but B increased from X to 3X. I know, guys, all you have to do is take a 3 and square it, and you get 9. So the answer is 9. Why did you have to square it? Because it's second order with respect to B, and we increased the concentration by 3. Okay. Now what if I increase the concentration of A? Increase the concentration of A. It went from Y to 2Y. So I doubled A and I tripled B. Then I would, since it's first order with respect to A, I just take 2 to the 1 power times 3 to the second power, and I would get 2 times 9. I would get 18, wouldn't I? Yeah, y'all see how easy that was? Right? Yeah, that was pretty easy, wasn't it? Okay. Number 10, the reaction A plus 2B yields products has a rate law. Rate is equal to A, what your rate constant times the concentration of A times the concentration of B cubed. So it's first order with respect to A, third order with respect to B. If the concentration of B is doubled, okay, while A is unchanged, by what factor will the rate of the reaction increase? So B is going to be doubled. So I know I'm going to take 2 and I'm going to cube that. I know 2 cubed is 2 times 2 times 2. And I know 2 times 2 is 4, and 4 times 2 is 8. So my answer is 8, D, right? Okay, so moving right along. 11, the reaction 2NO2. So I have 2 moles of NO2. They're going to react to give me 2 moles of NO and 1 mole of O2. It's suspected to be second order in NO2. Which of the following kinetic plots would be the most useful to confirm whether or not the reaction is second order? Okay, so remember, guys, we're going back to the integrated rate laws. If you recall from your integrated rate laws, if it's second order, if you graph the reciprocal of the concentration of a particular reactant, in this case NO2, you graph the reciprocal of it versus time, and if it's second order, you should get a straight line with a positive slope. Okay, the reciprocal. All right. If it's first order, you graph the natural logarithm. If you suspect it's first order, you graph the natural logarithm of the concentration of that reactant versus time. If you get a straight line with a negative slope, then it would be, of course, first order. Okay. If it's zero order, you just graph the concentration, right? Okay, so let's say a plot of NO2, okay, negative versus time. All right, so that of course is a reciprocal. The fact that I have that -1 right there. So that means I have 1 divided by my NO2 concentration, which is the reciprocal. So that would be the right answer, right? B, it wouldn't be the natural logarithm. That's what you do if it was first order. C, it wouldn't be just the concentration. That's what you do if you suspect it's zero order. Okay. And D, of course, is the natural logarithm of the reciprocal. You definitely wouldn't do that. And E is plot of to the concentration squared. Yeah, you wouldn't do that either, would you? Okay, all right. Now for the chemical reaction, A yields B plus C. A plot of A, the concentration of A versus time, is found to give a straight line with a negative slope. Okay, what is the order of the reaction with respect to A? We know if it's zero order, if you just plot the concentration of the reactant versus time, so in other words, the concentration is going to be on the y-axis and time is going to be on the x-axis. If you plot that, you get a straight line with a negative slope, you know that it's zero order, or zeroth order, I guess would be the correct terminology. Okay, so the answer would be A. Number 13, for the chemical reaction, A yields B plus C. A plot of the reciprocal of the concentration of A versus time is found to give a straight line with a positive slope. What is the order of the reaction with respect to A? We know if it's reciprocal, then you start thinking second order. Okay, so the answer, of course, is going to be C. Number 14, for the chemical reaction, A yields B plus C. A plot of the natural logarithm of A versus time is found to give a straight line with a negative slope. What is the order of the reaction with respect to A? And of course, we know that in this case, that coincides with first order, right? Okay. For a first order reaction, the half-life is equal to, we know that it's going to be the half-life is going to be equal to the natural logarithm of 2 divided by K. The natural logarithm of 2 is 0.693. So the answer to that is going to be A, right? All right. Now let's see. Number 16, the reactants A and B are mixed, and the reaction is timed until a color change occurs. The data are as followed. Okay. All right. So we have initial concentrations of A and B, and we have 3 different experiments. And they mark the time. So they said find the order with respect to A, with respect to B, the rate constant, and the units for the rate constant. So let's go ahead. So this is, of course, an initial rates problem. It's nothing we haven't seen before, have we? And I'm going to find the orders with respect to A, B. I'm going to find the rate constant and the units for the rate constant anyway. So let's go back to let's go ahead and do that. Okay. The reactants A and B are mixed, and the reaction is timed until a color change occurs. The data are as follows. Okay, so we know that our rate law is going to look something like this. Rate is equal to K times the concentration of A raised to some power. Let's call that M times the concentration of B raised to some power N. Okay. Now our job is to find M, the order with respect to A, N, the order with respect to B, and K, the rate constant. And while we're at it, we're going to go ahead and find the units for the rate constant. Okay, so I think I'll find the order with respect to A first. Okay, I'm finding the order with respect to A. So I'm going to choose 2 experiments. So this one, of course, is experiment 1, 2, this 2, and this 3. I'm going to choose 2 experiments where my B concentration stays constant. Okay, I'll say that again. In order to find the order, no pun intended, with respect to A, I need to choose 2 experiments where my B concentration is a constant. Okay, All right, so of course that's going to be 1 and 2. All right, so I'm just going to take, I can divide 1 by 2 or 2 by 1. It doesn't matter. I'm going to take rate 1, and I'll divide it by rate 2. I'm going to set that equal to, now I know that rate 1 is going to be equal to K times my rate, the concentration of A times raised to the m power times the concentration of B raised to the n power. All I did was I copied this. But I just put 1 right there. And at the bottom, I'm going to do the same thing. Okay, I know you guys can do that. Anybody can do what I just did. All I did was I found 2 experiments where the B concentration was the same. I'm trying to find the order with respect to A. And I just said rate that happened to be rate 1 and rate 2. I'm going to take rate 1 divided by rate 2. If you wanted to do rate 2, you could divide it by rate 1. You could do that also. It doesn't matter. So then I just write was on the left side, well, I should say the right side of the equation. I wrote that down twice. I wrote it in the numerator and the denominator. But of course, the numbers I put in here are going to go with experiment 1 in the numerator, and the numbers I put right here are going to go for experiment 2 in the denominator. Okay, so rate 1 was 0.04. If you guys want to leave off your units, you can. Okay, and rate 2 was 0.02. That's going to be equal to a K times, for experiment 1, my A concentration was 0.1. If you don't want to use brackets right here and you want to use parentheses, that's fine too. For B is 0.140. Okay, and I'm going to go ahead and put M right here, and I'm going to put N right there. So for 2, I'm going to put K. Experiment 2, my A concentration was 0.050 initially, and my B concentration was 0.140 because we purposely chose 2 concentrations, 2 experiments where my B concentration is the same. Now I'm sure you see now why we did that, because we get to cancel out the 0.14. It's in the numerator. 0.14 raised to the n power is in the numerator and the denominator, isn't it? So I'm going to go ahead and I'm going to cancel that out. While I'm in it, I think I'll cancel out my rate constants too, because I have a K in the numerator and a K in the denominator. Okay. Now, of course, you don't need a calculator to see that 0.04 divided by 0.02 is going to equal to, well, 2. So 2 is going to equal to 0.1 divided by 0.05 raised to the m power. So, of course, the 2 is going to equal to, of course, this is going to be 2 raised to the m power. So it's obvious what that m is 1, but we're going to pretend like we don't know that. Okay, we're going to pretend like we don't know that. We're going to use the power rule for logarithms. All right. All right. The reason why we're going to pretend like we don't know it is because it's not going to always be obvious what m is. So the log of 2 is equal to the logarithm of 2 raised to the m power. So this is where the power rule of logarithms come in. Anytime I'm taking the logarithm of an exponent, I can take that exponent out of the logarithm. So I'm going to say log 2 is equal to m times the logarithm of 2. Now, of course, I divide both sides by the logarithm of 2, and I'm going to end up with 1 is equaling m. So the order with respect to A is, of course, m. Okay? All right? So, yeah, if you guys need to take a snapshot of that before I erase it, now would be the time. Okay, or freeze it or whatever you want to do. Okay, all right, so now I know that m is equal to 1. I think I'll put that right there. M is equal to 1. So now I'm going to find n. Okay, the order with respect to B. Alrighty then, and I don't know why I didn't just erase that, but that's cool. So now I'm going to find 2 experiments where my A concentration remains the same. And of course, that's going to be experiment 1 and experiment 2. You don't have to at this point, since you already know what m is. I could just choose any experiments I wanted to, as long as it's not 1 and 2. And I could still find the orders. I just do the math. But yeah, since it's still, the math would be simpler if I just chose 2 experiments where my A concentration is the same. That's 1 and 3. So I'm going to say rate 1 divided by rate 3 is equal to K. I'm going to do the exact same thing I did before, just write this down so you don't confuse yourself, you don't leave anything out. Okay, go ahead and write it down, and then we go ahead and we substitute numbers after we write this down. I know you guys can write this down. Anybody can do this. All I did is I took this rate law, and the stuff that was on the right, I put it in the numerator and I put it in the denominator. Okay, so I'm going to say rate 1 was 0.040. Rate 3 was 0.010. Well, 0. There's another 0 right there, isn't it? Okay, it's going to equal to, let's see, K times my A concentration. For rate 1 was 0.100 to the m power times B, which is 0.140 raised to the n power. And for rate 3, well, experiment 3, my A concentration was 0.1, so I'm going to raise it to the m power, and my B concentration is 0.070 raised to the n power. Okay, all right, so of course we know why we chose two experiments where my A concentration was the same, because I have 0.1 to the m power in the numerator and the denominator. I get to cancel those out. While I'm at it, I might as well cancel out my rate constant. And let's see what we get here. I'm going to have 4, because 0.04 divided by 0.01 is equal to 4, is equal to 0.140 divided by 0.070 raised to the n power. Okay, so of course, that's a decimal sign right there. 0.14 divided into 0.07 is 2, so I'm going to say 4 is equal to 2 to the n power, and it's obvious that n is going to equal to 2, but we're going to pretend like we don't know that. So I'm going to say the logarithm of 4 is equal to n times the logarithm of 2. So I'm going to say the logarithm of 4 divided by the logarithm of 2 is equal to n. All right, and so, and of course, let's see, the logarithm of 4 is equal to 0.60206, and the logarithm of 2 is equal to 0.30103. Okay, and what did I was supposed to put n right here, wasn't I? Yeah, my bad. Got a little ahead of myself there, didn't I? It's equal to n, so 2 is equal to n. Okay, so I know the order with respect to A is 1, the order with respect to B is 2. So now the only thing that I need to do now is go ahead and find the numerical value for my rate constant. I know the units for the rate constant because it's third order overall. Since it's third order overall, I'm going to end up with units of m to the negative 2 s to the negative 1. We take 3 minus 1 would be 2, so this m to the minus 2 s to the minus 1. Okay, but I don't have the numerical value for the rate constant. I can choose any experiment I want to find the numerical value for the rate constant. Okay, I'm just going to write rate is equal to that constant times my A concentration raised to the 1 power times my B concentration raised to the 2nd power. Okay, at least I think that's what it was. Yeah, B is second order with respect to B. So let me go ahead and put a 2 right there in lieu of that n that I just put up there. Okay, I'm going to put a 2. Ah. Okay, so I'm going to say rate is equal to 0.0400. Okay, now if you want to actually put the units in for a rate and the units in for the concentrations and solve for the units of K, you're going to get the same thing. Okay, you're going to get, let's see, m to the negative 2, s to the negative 1. But yeah, if you just remember it, I guess it should be, you'll be fine. So I'm going to say, so for experiment 1, my A concentration was 0.100 times my B concentration, which is 0.140, but I'm going to square that because it's second order with respect to B. So I'm going to say 0.0400 divided by 0.100. I'm going to divide that by 0.140 squared, right? That's going to equal K. So let's go ahead and find out what K is equal to. 0.04 divided by 0.1 divided by 0.14 and divide by 0.14 again. And I'm going to end up with 20 point, let's see, how many significant digits is this good to? 1, 2, 3. It's good to 3 significant digits. 20.4. Okay, so 20.4 m to the negative 2 s to the negative 1 is equal to k. Now again, instead of writing m to the negative 2, I could say liters squared per moles squared per second, okay, is equal to k. All right, so let's go ahead. So it's first order with respect to A, second order with respect to B, and the value of K is 20.4, and the units for K is liters squared per mole squared per second, or m to the negative 2 s to the negative 1. So let's see if we got that right. Let's look at number 16, 20.4 m to the negative 2 s to the negative 1. Yeah, so yeah. All right, so yeah, let's go ahead and take a look at number 17. For a reaction, A yields products is second order with respect to A with a rate constant of 0.547. Well, it's second order with respect to A, so that should be m to the negative 1, s to the negative 1, and I left that off there, didn't I? Let me change that. Well, I'm going to have to change it later. All right, because, okay. In an initial reacting concentration of 0.0127 moles per liter, what is the concentration of reactant after 180 seconds? Okay, now I should have put a first order one, integrated rate law problem down here too. I should have done that. Yeah, I think I'll think of one while I'm at it before I leave, because you guys, y'all need a first order one too. Okay, but I guess I might as well do this one. I'll go ahead and do this. Okay, so it says for the certain reaction, A yields product is second order with respect to A with a rate constant of 0.547. It should be m to the negative 1, s to the negative 1, by the way. And an initial reactant concentration is 0.0127 moles per liter. What is the concentration of reactant after 180 seconds? So I'm going to write my second order integrated rate law because it's suspected to be second order with respect to A. So I'm going to say the reciprocal of my A concentration at times T is going to be equal to a positive KT plus the reciprocal of my initial A concentration, or A sub 0. Okay, so that's my second order integrated rate law. All right, so now all I got to do is plug things in, and of course I'm solving for the concentration of A at times T, so I should have numerical values for everything else up here. Okay, so my rate constant is 0.547, okay, m to the negative 1, s to the negative 1, times my time, which is going to be 180 seconds, plus 1 over my initial concentration was 0.0127. Now, let's look at these numbers, okay? Now, if my initial concentration is 0.0127, that means my final concentration after 180 seconds has to be less. We know the concentration of my reactant is going to decrease over time. So it's going to be less, so we get to find out how much less. Now, notice I have seconds in as a variable for my time form, and I have reciprocal seconds in my K term, so they're going to cancel out, aren't they? All right. So when I get 1 over A at times T, it's going to be equal. Let's see. So I'm going to say 0.547 times 180. I'm going to end up with 98.46 liters per mole. Okay, because m is moles per liter, so m to the negative 1 is liters per mole, plus the reciprocal of 0.0127 is going to be 78.7. Well, let me see. It's only good to 3 significant digits, isn't it? 78.7 liters per mole. Okay, and this one is only good to 3 significant digits, so I'm going to make that 98.5. All right, the reason why I have to report it to the correct number of significant digits right now is because I'm about to add these two terms together. Okay, it was before I multiplied and I took a reciprocal right there. Okay, so I'm going to say 98.5 plus 78.7 is going to give me, let's see, 177.2. Okay, m to the negative 1. Now, I know you're saying to yourself, well, you have more significant digits than you started off with. Yeah, that's fine. Remember, we're adding. So I started off, both numbers had 1 digit to the right of the decimal point. So my answer is good to 1 digit to the right of the decimal point. The rules for addition and subtraction are different. Okay, so now this is not my answer. It's the reciprocal of my answer. In order to get my answer, of course, I'm going to end up with 1 over 177.2 is equal to my A concentration at times T, my A concentration after 180 seconds. So the reciprocal of that is, of course, 5.643 times 10 to the negative 3 moles per liter. Okay, so that's 0.005643, and that, of course, is indeed smaller than what we started off with at 0.0127. Okay, all right. All right. Okay, now I'm going to do a first order integrated rate law problem. I know you're saying to yourself, well, it's not on the study guide. It should have been on the study guide, and it'll be on future study guides. I'll just take this same reaction. For a reaction, A yields product. I'm going to say we're going to assume that it's first order with respect to A. First order with respect to A, with a rate constant of 0.547 reciprocal seconds. Okay, you leave the liters per mole off. It's just going to be reciprocal seconds. All right. Okay, if an initial concentration is 0.0127, we're going to leave that the same. What is the concentration after 180 seconds? So I'm going to write my first order integrated rate law problem up here. I'm going to say the natural logarithm of A at times t is equal to a negative kt plus the natural logarithm of my initial A concentration. Okay, all right. All right, now all the other first order integrated rate law problems that we've worked up to this point, you've been asked to find the time. Okay, that's pretty easy. All right, this one I'm asking you to find the concentration. All right, so I'm going to say the natural logarithm of A. It's a little bit more complicated. The algebra is a little bit more involved, but you guys are going to see it's nothing you can't handle. Okay, so I'm going to say a negative. And I'm going to say my rate constant, in this case, is still going to be 0.547, but it's going to be reciprocal seconds. That's the units of the rate constant. The units for a first order rate constant is going to have reciprocal seconds. I'm going to say 180 seconds plus the natural logarithm of my initial A concentration. All right, so far so good. All right, so just like before, I'm going to multiply 0.547 times 180, but I have this negative term in front of it. So now I'm going to get a negative 98.5. Okay, and I'm going to end up with a unitless number because I have reciprocal seconds right here and I have seconds right there. Plus, go ahead and take the natural logarithm of 0.0127. I love you, man. All right, so I'm going to end up with, make sure you report this to the correct number of significant digits. Okay, so I'm going to end up with a negative 4.366. Let's see. Yeah, negative. So yeah, I end up with an extra significant digits, right? Uh, my characteristic has to have 3 significant digits because this is good to 3 significant digits. Okay, so I'm going to say the natural logarithm of a at times t is equal to, now I still have 2 unitless numbers, so I'm going to take, let's see, 98.5 plus 4.366. I end up with a negative 102.866. Now this number is good to 1 digit to the right of the decimal point, isn't it? So I'm going to go ahead and round that 8 up to a 9. So I'm going to say the natural logarithm of a at times t is equal to a negative 102.9. Okay, now, okay, I'm trying to find the concentration of a at times t, not the natural logarithm of my a concentration at times t. So if you guys, well, I guess you guys wouldn't know this, but this is the way you do this. You just say a at times t is equal to e raised to the negative 102.9 power. All right. So in other words, all you got to do is hit the anti-natural log key, which is the second function key. So that natural logarithm key, just hit the second function key and hit that key. And then you're just going to put a negative 102.9 in. And you're going to end up with your A concentration at times T is some ridiculously small number, is 0.0469. All right, times 10 to the negative 45. All right, so let's see. All right, and apparently this is only good to 1 significant digit, right? Is that right? So, so let's see. Yeah, it's only. So I'm going back the other way. So yeah, I guess it's only good to 1 significant digit. So it'll be the answer would be 2 times 10 to the negative 45 power. So yeah, apparently your concentration just decreases like you wouldn't believe after 180 seconds. Let me see. I think, did I do anything wrong? I think I did something wrong. Yeah, let me make sure. 98 natural logarithm of 0.0127. Yeah, that's right. 0.5 plus 4.366. That's 102. It's negative 102.9. Yeah, e to the negative 102.9. Yeah, that's right. Yeah. Okay. Well, I guess that's why you just don't make up integrated rate law problems on the fly. But yeah, if it were a first order one, then that's what it would be. Okay. So yeah, I think that's the study guide. I think that's the entire study guide. So yeah, and plus one extra problem. So the answer to number 17 was, what is the concentration after 180 seconds? When is second order? Let's see. I have 5.63 times 10 to the negative 3. 1643. Yeah. So yeah. All right. So guys, good luck on on your test. Okay. All right. And I will. Yeah. So I'm signing off now.